Thanks you all for coming today. This is our last workshop at the DSI for fall quarter. So I'm just going to give a quick bump. My name is Pamela Reynolds. I'm the academic coordinator here at the DSI. I'd love to get your suggestions about future workshop topics. So if you go to the DSI website, Jane, would you mind? Yep, great. And if you click under events and workshops, you'll come to a page here that'll have a link to a form where you can actually suggest topics. If you have to be signed in through your UC Davis account or the form throws an error. But you can also email us at datascience@ucdavis.edu if there are topics. Don't worry if they're a topic that we've taught before, and we will go back and repeat things. But if you want to know about what we have taught, one of the easiest ways is to go to events and then to categories and then search through the workshops and the other event listings that are on that page there. And we do record, so that's just a heads up for all of you today. We are recording in the back, so if you don't like the tops of your head to be visible, feel free to move toward the back of the room. And with that, I want to introduce our instructor today, Jane Carlen. She is a postdoc here at the DSI who has her PhD in statistics and a background in network analysis that she worked on for her dissertation. And I'll also put in a plug that if you want to learn more or have questions about what she talks today to you about, she has office hours weekly, and currently they're Thursday afternoons. They probably will change for next quarter, but you can find out all of that if you go to the homepage on the DSI website. All right, thanks, Jane.
Thank you.
Sorry, very last thing I forgot to mention, pink stickies. If you run into problems today, feel free to stick them on your computer, wave a hand. Myself, our other postdoc, Dan Hicks, our staff data scientist, Arthur Kield in the back, we'll run around and help you as we can. Okay, that's it.
All right. So let's get started. So yeah, I put everything on this GitHub, so you can just clone, or actually you probably don't want to clone it. It's not going to change in it after this. Download it, put it somewhere, and then open your, is everyone here using RStudio today? Okay, cool, so it'll all look the same. And here, let me actually, I'm gonna get this final document. Oops, it's in a different place for me. All right. Okay, so this is the output of this markdown that you should all now be looking at. So the markdown is in the repository. Once you download it, navigate to it, open it. Who is now looking at the top of this markdown document in RStudio? Okay, so a couple people not there yet. Let me give you a second to get over there so we're all on the same page. For the people who are already there, you can, also in the repository, there's a file called packages to install. So this is everything that I thought you might not already have installed that we will use at some point. It's not necessary to install it all right now. You'll probably already have some of these, but here's the list. So if you're like, I know I don't have that package, you can install it now while you're waiting. All right, let's see if everyone's kind of getting where we are. Is anyone having trouble getting there, opening it up? Okay, looks like most people are good. Like I said, we can install the packages as we go. All right, so now we have everything. And again, this is the output of that document, which is, I've already run. Let me first go over what my goal is for today. So there's a lot that you can do with networks, and there's a lot you can do with networks in R. Obviously, I can't cover it all today, but my goal is to go through probably the two main package kind of in their ecosystems, which is the statnet packages and then igraph. And igraph also has a version in Python for Python users. Those are the two biggest things I want to hit. And then I'm going to cover this latent net package, assuming we have time. But the talk is organized basically by package, and I originally thought about organizing it by kind of task, like here's how you load different networks in different packages, here's how you visualize them in different packages. But then I thought that's not actually how these packages kind of develop. They kind of developed as their own little mini ecosystems, and even if they don't have like the best visualization or they don't have everything, they kind of each have a workflow from start to finish. So it kind of makes sense to just go through one, see how you'd use it, and then go through the other one, see how you'd use it. And then you can always switch back and forth if you need to use something that's not in your given package. And then there's these visualization packages now kind of on top of the basic analysis packages that you can use as you see fit. And we'll go over a couple of the visualization packages in the process of what we're doing. Okay, and also I should say this is very biased to my experience. So I used ergoms a lot, which we'll talk about what those are. And for my dissertation, I used latent space models in my dissertation. So I especially use these two a lot. I used igraph a little bit less, but it's very commonly used, so it makes sense to include it. But yeah, this is in no way meant to be a completely representative tour of network analysis in R. It's sort of my representative tour. Okay. So, oh, and even though this is about network analysis, I know some people here are relatively new to R. So again, please feel free to ask questions, even if it's just an R question, either to me, to Dan, to Arthur. Okay, so to get started, here's, now that you've hopefully installed some of what you need, again, this packages to install has the list. You can load all these packages now. I actually don't recommend it because there are name conflicts between these packages. They have a lot of, not a lot, but some of the same function names, like the degree function. So it actually probably makes sense to just load as you go and then reduce the name conflicts. Oh, and also, so set in RStudio, set your working directory to wherever you put this repository. So you want to be in the top level of the repository. So something like this for me. But whatever it is for you, that should also reduce problems later. Okay. So also, before we really dive in, just sort of a list of terminology, which I'm going to use a lot and pretend like you're already familiar with. But the list is always here if you need to refer back to it. So just going through really quickly, we're talking about networks. Sometimes they're referred to as graphs. There's no real difference. Nodes are the elements in the graph or network, or they're also called vertices, and then you have edges connecting them. A binary network is where the edges are just 0, 1. Directed is you can have one edge from node I to node J, and you may or may not have an edge from J back to I. Versus in an undirected network, there's just one IJ pair, and it's either on or it's off. And we'll see examples of both. A dyad, I probably won't use that term very much, but it basically refers to the whole thing. So the two nodes and whatever's between them. So that's one edge if it's undirected and two directed edges if it's a directed graph. Bipartite network, we'll cover that a little bit, but the idea is that you have two distinct groups of nodes and they don't connect within themselves. So a good example would be heterosexual sexual relationships. You have women and men connecting, but not men to men and women to women. The adjacency matrix, we'll also use that a lot. That's just the matrix representation of the network. So like Aij would be 1 if there's a binary edge from I to J, and that matrix is symmetric if the network is undirected. And last, an edgeless representation. So you can also represent a network as just the list of the edges that you have. And especially if you have a very sparse network, so there's very few edges relative to the size of the network, it's a pretty small way to represent your network, as opposed to the adjacency matrix, which could have the full number, n by n, and most of them would be 0. And you can use a sparse matrix representation, but sometimes an edgeless is faster. Okay, any questions about that before we dig in? Okay, so our first package is statnet, which is actually really a bunch of packages. So it built out of the need to use exponential random graph models in R. And then it's gone a lot of places from there, and there's a lot of variations of exponential random graph models. Before I explain what an exponential random graph model is, just sort of say there's a few key authors that are associated with this statnet family. This, and probably there's a couple more, but when you kind of see those authors, you know I'm kind of dealing in this, potentially in this ergom world, or in a statnet related package, because there's a lot of them at this point. Here's just sort of a list. Where is it? Here's just a few, right? So obviously some of them have the word ergom in them and they're easy to identify, but like epi model, which Goodrow and others wrote, I think Morris, wouldn't necessarily stand out to you as an ergom-based package, but it is. So, and then, yeah, there's all this whole ecosystem of other related packages, SNA, statnet, ergom, it's all in this family. Okay, so what's an exponential random graph model? It's a pretty simple model to state. It basically says the probability of observing some network Y, given some covariates in X, the size of the graph, so that's fixed, which is N for N nodes, and then some coefficients, is just this simple expression, an exponential of like, you know, something similar to a regression model, where you just have T would be like a statistic that you measured on the graph. So it could be like the number of nodes that have a certain characteristic, and then a coefficient on that. So just the exponential of that. And then C is just a normalizing constant to make this thing a probability distribution. So it's basically the sum of all the numerators so that the whole thing will sum to 1, right? 'Cause we need that to be a probability distribution. So again, very simple to state. And you can think of it almost like regression for networks, except that it doesn't always work and it's a lot more complicated. But just in this idea of having, you know, this simple expression of, you know, coefficients, statistics, and there's a ton of flexibility. So one of the strengths of ergom is there's a ton of flexibility in the kind of statistics that you can measure on a network. So these T's could be a whole range of things. They can use nodal covariates, they can use edge covariates, it can be a function of both. A couple examples would be like number of edges in the graph, which we almost always include unless we fix the number of edges, number of isolates, number of edges whose endpoints match on a certain covariate. Another selling point of these models is it's the maximum entry distribution on graph space. So basically it just says, you know, I'm given my observed statistics. I want a distribution over graphs where the expected value of those observed statistics is going to, expected value of those statistics is going to match the observed. And then this distribution gives me the least additional information. So that's cool. Now, where do we run into problems? This C is basically impossible to calculate directly for non-trivial sized graphs. The number of possible graphs is enormous. You can't just calculate it directly. So that means that to do inference on these models, you generally have to just explore the parameter space using something like MCMC. Draw samples and then optimize from there, which can be very slow. And it also sometimes just doesn't work at all. So there can be degeneracy in the estimation process, like I can't really explore the space using this sampling method, or there can be just degeneracy in the model of itself, where basically it satisfies this property that I set up this distribution and I know the expected value of my statistics is going to match the observed. But it does it in this really weird way sometimes where it's basically like an average of empty and full networks where I get the right average so that it matches and it works out. But if I simulate from the model, the simulation wouldn't even actually look anything like my observed graph, which is not a good quality in a model in general. So, so to summarize, very useful flexible model with these issues of degeneracy that you'll have to deal with, and I spent a couple of years of my dissertation trying to tackle them. Okay, so, and the last thing to say is they're generally used for smaller networks with some exceptions. And that's probably, they kind of grew out of these social network applications where, at least before social media, which is when they started, these models started to come around, your human social networks usually were pretty small, what you'd actually measured. So they were kind of built with that in mind. You generally wouldn't, unless you have certain qualifications, you probably are not going to run an ergom on a network with thousands and thousands of nodes. Okay, so without further ado, so you guys can start doing stuff and not just be listening to me, we are going to look at an example network of Supreme Court decisions about the First Amendment, which was supplied by one of our guests today. So thank you for that. So they gave me this data. So it's decisions by the Supreme Court from 1994 on that relate to the First Amendment. They said they were interested in this patterns of homophily, especially if justice characteristics are associated with justices deciding in a similar way. So like gender, age, religion, do we see homophily or sort of similar behavior based on those characteristics? Okay, and then we'll also probably, if we want to look at these characteristics, we somehow need to control for other important characteristics like the party of the appointing president, because obviously you'd expect judges appointed by Republican versus Democratic presidents would behave differently, so we need to control for that. Okay, and then here's a picture for you to look at. So they said the data starts in 1994 because that's the first year with actually more than one female Supreme Court justice. We need more than one to start looking at homophily on gender, right? So. Okay, so let's get started actually using statnet. So let me go over here for a second, down to where we are. This folds up. Line 131. Ooh, yes. Okay. All right. So you should be here. So if you put yourself in the right directory, you should be able to enter that and it should work for you. I'm not going to do it because I've already made some modifications. But so if you enter that line, is that loading? Is anyone having problems loading this data? All right. So you should get out some, when you do this summary of the edges, you should get something that looks like that. So look up if you are there. Okay, I'll wait another second.
What's the line code?
131, 130, for me it's 137, but generally over here. Oh, set WD, and then in parentheses, in quotes, path name. Let's see where people are. If you've already done this step, feel free to just keep going on the code. Yeah.
Do I need to download those files first?
So if you need to download the repository there if you haven't already. Yeah. Yeah.
I think there's nothing about her.
Okay.
Where do I go from here?
Okay. Is that if you okay? Click command enter.
Sarah, I'll just look over someone's shoulder and watch them do that.
So you need to oops, sorry.
No
Install. Oops. Okay. Install packages of statnet. And anytime you see that message, you're gonna have to keep doing those. Sure. Let's see. Let's just see that. Okay, let's just try that. You might run into another problem later, but
Fingers crossed. Thank you.
and I guess I haven't put a bench. Maybe I'll share the output. Maybe I don't know. Sorry, that might not be true. How is this working for people? Oh, yeah, you got it?
No, this is Arthur's computer.
Oh, wait.
Arthur's
Oh, that's Arthur's computer. Oh, okay. Oh, okay.
Yeah.
Is anyone not getting it to work where they think it should be working? Yeah.
So how do you put? So you have to define WD.
Oh, yeah. So SETWD. I'll write it up.
Okay. And now try versus that's the same.
Yeah. No. I have the output. I would not recommend doing it. It'll take a few minutes. You can, I guess.
Well,
but yeah, we're
I
just
do it line by line.
yeah.
I don't actually really work with NetR at all.
So you can basically select lines and that command or whatever it is on Windows and enter them. Yeah.
I'm getting this RS scalar here.
Set attribute on a symbol. So almost all of these errors, let's see. SETWD. Oh, but you have, so that's not working?
I guess not. Well, I've never seen it here before. That doesn't seem good.
I'll come back. I'm not sure what that shouldn't happen. Yeah.
10 days, you know, I understand it.
Anyone else? Yeah.
What is this one?
WG not found. If you go up to the further here, it's kind of hard to see. If you go up to like the first first chunk here. Okay, so at the bottom there. So I set my WD being working directory. I set it for my system. So you're going to want to set that for wherever, like to point to the repository that you downloaded.
Do you have, do you have to start from C?
Yeah, on a PC, yes, I think so. Or you can start from whatever directory you're in.
So if I have the data saved right here.
You can also, here, how about, let me show people. So I think some people are just running into problems because of the directory. If you can easily get around this, go to session, set working directory, choose directory, and then navigate to wherever you downloaded this folder. And that's the one you want to be in.
Okay, it'll take a couple of minutes.
Thank you. That work, hopefully.
I just changed it.
And then actually, so then because of how, once you set that, yeah, so once you set that, because of how I set this up, then go into the console once you set that and type GETWD, okay? And that's now where your working directory is. It should end with this, network analysis in R.
Yes.
And then the last thing is type WD equals, and then that last thing that you just got. because I'll refer back to this WD variable later in the code, so we just have to make sure everyone has it set. So again, it's you go to session, set working directory, choose directory, navigate to the folder, network analysis in R, then see where it is with this function, and then save that as WD.
So it should be like this.
That should, let's see. So we can check this way. Yep, that looks good. And then also let's do WD equals that thing in quotes. All right, is everyone good? Have their direct, if this is all set up correctly, then this line of code should run without a problem. So is everyone getting that line of code to run, or at least 75% of you? Yeah. R? Oh, I mean, I assume everyone has the latest version. Yeah, I would. Yeah, I'm running the latest version, so. Does anyone else have any questions about this? Yeah. Sorry. No, it's good. You didn't do the last thing that WD equals. Equals, and then in quotes, whatever your working directory was. If you, so actually, before you do that, so just do that GET. Sorry, it's not super easy to see up there, but this is your working directory. So now WD equals this. Okay, now it should work. The read CSV. Oh wait, hold on a second. Wait a second here. It should end with network analysis in R.
Okay, so I found the file.
Did you download? So go back to here.
So here's the file that you're using, but I can figure out how to download this.
Yeah. So go to the click here. And then just click here, and that'll give you everything you need.
Okay, so I downloaded that in the zip file, which here, I guess I should figure out that was the file.
That's fine. Okay, cool. So now if you go back into our studio,
This one.
that's the file you were going to be using. But if you go back into our studio and you do session, set working directory, choose directory, and then you navigate to that folder you just downloaded.
This one?
Yeah, there. Yeah, just, okay. Okay, now. Great, okay. Now, last thing, WD equals this, and now this should work. Yes, no, why? String constant. What are you talking about?
I just copy pasted it.
Oh, okay. So then open. Fingers crossed.
So I didn't load. I loaded the statnet, but I didn't load igraph in it.
Okay, it shouldn't actually come up. It shouldn't do that right now. I think it might have tried to run a little too much code. Just that.
There we go. Okay. So now, so actually, sorry, oh no, it is right. Yeah. So that last slash was just missing that last time. But now it should all be good now. You should be able to keep going line by line. Yeah. All right. All right, so let's keep going. So I'm going to assume everyone is able to run this line of code successfully now.
The last slash.
Or they're just deciding to look on with their neighbor for the rest of the time. But if you're still having problems and you really just want to get caught up, Pamela will just raise your hand and Pamela will help. Okay, so we should have this thing called SC for Supreme Court edges. And then we also should have this other one, SC nodes. And then do the summary commands for each of them. But we'll start with sc.edges, and you should get out something that looks like this. So this is basically just to look at what this data is, right? So someone sent me this data. I was like, I don't even know how it's structured. I need to look at it first. So we have a source, a target, whatever those are. We'll figure that out in a second. Some opinion information, like was this line referring to concurrence, dissent, etc. And then a more general type, kind of coarser graining than opinion information, some IDs, case names, which we won't use very much. But it turns out that, so if you look at this source, it goes from 1 to 14. And if you look at target, it goes from 15 to 190. So it actually turns out that the source refers to a judge, and there's 14 judges in the data set, numbered 1 to 14. And the target is like the decision. So there'd be like 176 unique decisions. So that's not just like, that could be like the dissent for a specific case, the concurrence for a specific case, etc. So that's how it's structured. And then the nodes gives us some more information. So actually, if you look, so if I do, if I look at the first 20 rows of that node, you'll notice that actually after 14, it just starts being blank. And that's because this is only giving us information about the judges. So and there's only 14 judges. But it's giving us some interesting information. So name, gender, date of birth, religion, detailed religion, when they were in the court, the school they went to, and we'll use a bunch of these variables in our analysis.
So could you just go back to what?
Yeah.
So just repeat what you just go back to
about this
slide. So you have the source and the target, and then how did you get to the next thing from the source?
So this next thing was just a summary of the nodes instead of the edges. Yeah. No. Okay, so this is the data that we have to work with. And so that means that this is first structured as a bipartite network, right? Because we have these sources, 1 to 14, that connect to targets that start at 15, and we never have source connecting to source or target connecting to target. So I was like, oh, that's cool. I don't really work with bipartite networks very much, but here's an example of one. So yeah, just kind of describing that. And then I actually, instead of using the detailed decision information, I used the information in type to kind of classify the decisions, because it's a little coarser, and I wanted more edges between things. So we have this, this next code block. You can just run it. You don't really have to understand exactly what it is, but all it does is just make it so that I'm going to be using, instead of the full list of decisions, I'll use the coarser list. So 176 drops to 113. Again, don't worry too much about the details here. Just run this code. So now you should have this, if I enter, this
in the console, right? I should get something out. All these variables should be here. Or if I do head, just to make sure we're all following along.
That's the thing, for every like function, you need a
I think probably people are needing dplyr at this point, so if you haven't already, if you haven't already done that, you probably want to do that. Yeah. Yeah, so it means this. So so again, everyone just make sure you have installed this dplyr. So run this if you haven't already, or you don't already have it on your system. And then if you're not sure if you already have it, start by doing this, library dplyr. If you have it, it just does nothing. If you don't, it'll tell you, I don't have that. And then if you don't have it, go back and install with this. Yeah.
I already installed it, but if I do the library list, it's very thankless.
That's fine. Yeah, that's okay. So now it's saying source is unknown. But are you sure? Because you haven't created, so you have to go back. Go back up a few lines where it started. Oh, actually there. Yeah. Did you? Can you go back to the markdown document? Do you have it loaded here or opened here? Oh, you should open it in there.
I open it under here.
I would open it in here, actually. It's just a little easier. So just from here, go File, Open, yeah. Yeah, no. Yeah, let me come around.
So I thought I'm having trouble installing dplyrs that's working. When I run this,
Say yes.
yes.
Yeah, yes to all of it, yeah.
Yeah, so I say yes, and then a bunch of warnings come up.
That should be okay.
And then when I come here and want to run this one,
And then it's not, well,
it says,
do you have the latest R and everything? Do you,
I don't know how to find it.
I think it's R.
Okay, so I think you're a little behind. That might be the problem. Yeah, I think they're at like 3.5. Yeah. Sure. Okay, sure. First, well, so should I keep going or make sure everyone has the data? Okay, because I think some people are still don't. Okay, who else is, okay. Okay, so do we have, you have SC edges, okay. And now, this is something.
So, in Windows, to differentiate, but that's also a set. So just double every backslash you see.
I think the read.
Okay, so now that you're actually exactly.
Okay, so I think we need to. No. Okay, here, let me have you type this. So delete that. I think what's happening is try changing sep equals to a comma.
Yeah. Now you should be able to run this.
Okay, enter. What?
Yeah, so the issue here, I think, is you need to put 2 backslashes at the end of both of these.
Okay.
Just so that the data is in a different directory. Okay. Great.
There's like an extra.
Load it in.
Yay. Okay. Thank you.
And then you run that condensed stuff.
Okay. Let's see now. Do head and then sc.edges.
You need to include at the beginning of this file. There's a whole bunch of libraries.
Okay. Now it should work.
Run that bit of code where it loads in this.
Okay, so I guess it's a system-based thing, but it seems like some people. So when if you've loaded an sc.edges, it should look like this: source, target, etc. If you're getting weird commas, is anyone getting weird commas?
I was.
You were. Okay. Anyone still getting weird commas? If you are, you might need to change this sep to being a comma. If not, don't worry about it. Okay. All right. Anyone else having trouble still just getting to this point where you have sc.edges, or now we're trying to get sc.edges condensed? Okay, so make sure we're all on the same page. If you type head, so this line of code in your console, head of sc.edges.condensed, comma 10, you should be getting the first 10 rows of this condensed thing, which I'll explain where we are in a second with that. And it should look something like this. Okay?
So if you're not getting that, raise your hand and Pamela or Arthur will come around. Okay, so I'm going to assume everyone has this data now. We're all together. Okay. Okay, so now we've kind of taken a little detour in getting everyone set up. So let's go back again and say what we are, what this data is, and what we're trying to do. So we have 14 judges, Supreme Court judges, and information about them, which is contained in the sc.nodes data frame. We now have a more condensed list of decisions. And we're going to, so an edge in our network is going to represent, at least to start with, a connection from a judge to a decision that they were on. So it could have been like, you know, the dissent opinion on, you know, Brown v. Board of Ed or whatever that case isn't in this data set, but it's the first one I thought of. So that's, to start with, that's the edges in our graph, right? So nodes, the full set of nodes is actually judges and decisions, and they can be connected, right? Later, we're going to condense the nodes to be just the judges, which is why I'm sort of referring to the judges as the nodes. But for now, with our bipartite network, judges connected decisions. Okay. So finally, we can actually start to make a network. So let's start. Our number of judges is 14. Ignore that warning. Our number of decisions should be, hold on a second. Let me actually get on the same page as you all. Okay, so n.decisions, if I now look at it, it should be 113. Because I've just entered these two lines. Is everyone getting that? Okay, and now the magic, we're going to create the network. So we're calling it sc.bipartite, and we're going to use the network function. So from the network package, which is basically part of statnet. And what we're using to create the network is just this list of source to target, right? So we're basically creating this from an edge list. Source being the judge, target being the decision. And then our number of, because we're doing a bipartite, you look in here, the bipartite kind of tells it what's in one set, because again, bipartite network means I have these two distinct sets of nodes. It basically tells it like what's in one set, what's in the other. And I'm also, when I create this, just reformat this so it's a little more visible. There we go. So actually, okay. So when I create this thing, in addition to the edge list, that I gave it, I'm also going to give it attributes about the vertices. So I'm breaking breaking the vertices into these two groups here. That's what's happening here. I'm adding the year of the decision. And I'm adding names of the cases. So these all look a little weird because I have like case information, right? I only have that for the decisions. I don't have it for the judges, or the name of the judge, which is here. I only have that for the judges. I don't have it for the cases. So that's why all these like vertex attributes are kind of these weird concatenated two things, right? Okay, so is that working for people? If you type in sc.bipartite, you should get out something like this. where you see, okay, you've created a network. So this code is a little like wonky. We don't need to go into the details exactly of it now. That's for you to kind of mull over later. But the important thing is we created this bipartite network and gave it attributes. So we should see all that reflected in sc.bipartite over here. So we should have 113 vertices. So it's just counting the decisions. We should have bipartite. So that's like the other set of nodes, 14, that represents the judges. Total edges, right? So that's all the connections between judges and decisions, to be 426. And then we should have these vertex attributes. So let me just look at one. So one way in the statnet world, one way to look at a vertex attribute of a network is to type in the network name and then do this weird %v%, and then the attribute that I want. So I'll use label in quotes. And let me press enter. Right, so the last bunch of entries is just blank because the decisions don't have names, but the first 14 are the names of the judges. Yeah.
What did you type?
Oh, it was this sc. After I ran this code to create sc.bipartite.
Yeah, I just can't read it.
Oh, sorry, sc.bipartite %v%, and then in quotes label. Are people seeing this this vertex attribute? Okay. Okay, so I'm assuming a couple people are probably still struggling with that, but in the meantime, let's give ourselves something to look at. So just select this entire block of code that starts with plot and run that. Okay, and you should get something that looks like this. It's kind of a mess. Yeah, don't worry. This will be probably the worst visualization we make the entire time. But yeah, I'm going to go back up to the code in case anyone's still struggling with that. But if you've gotten this plot to work, take a look at it, try to figure out what exactly is going on with it. Yeah. Oh, it comes down here. Oh, yeah. If you run this is kind of a weird thing about Markdown. If you like select this whole plot and you run it, you press like in a Mac, you press Command Enter, the plot will show up below the chunk, versus if you cut and paste it into the console, it'll show up in this other window. Just something to be aware of. Oops. Unless the figure margins are too small, right? So for the most part, if you're just following along, you'll probably be, the plots will come below the chunks. Okay, so is everyone looking at this ugly plot now with me? Okay, again, Pamela and Dan will help if you're still, if the data is being wonky. But yeah, this is a really ugly plot. But I mean, I guess we see some things. So we kind of see this mess of judges in the middle, and then all these decisions. So the judges are these large black nodes. The decisions are the triangles. And since there's so many decisions, and in general, each decision doesn't have very many edges, the default plot layout just says, okay, I'll put all the like minimally connected things on the outside. They're colored. It's hard to see up here, but maybe on yours you can see they're colored, depending on if it's concurrence, descent. I looked at this for a while. I don't really like get a lot out of this plot, to be honest. But if you see something cool from it, that's great. But what this leads me to say is, like, for my purposes, I don't really care about the bipartite network. I would much rather have a network where instead of judges being connected to decisions, I have judges connected to judges if they were agreed on a decision, right? That would probably be a lot more useful for me, especially for my analysis questions of seeing when judges make similar decisions. It's also going to be a lot easier to visualize. So, so basically, I'm kind of done with this bipartite network. I want to make a unimodal network, or what I normally think of when I think of a network where anything can connect to anything. So how do I do that? So I've created this plot. Okay, so I'll skip the aside, but I was very disappointed to find out that this insanely hard problem that Will Hunting solves in the movie Good Will Hunting is actually a very easy graph theory thing that we're about to use. So it turns out, so okay, if I think about, please sign in if you haven't already. So if I think about my current bipartite network, I have judge 1 connects to decision 1. And if judge 1 and judge 2, if they agreed on this decision, they'll both be connected to this decision, right? So if I want to know the number of times that judge 1 and judge 2 agreed on decision, I actually just need to find these like 2-step walks from judge 1 to judge 2. And in my current setup, I don't have any connections between judges, right? So any 2-step walk would have to go through a decision. So if I have a method for finding all the 2-step walks from one thing to another, I've actually now found the number of times that 2 judges were on the same decision. So that turned out to be really easy. So all I have to do is take the adjacency matrix from the bipartite network and multiply it by its transpose. Great. So I'll do that. So this function, you might say, well, I don't know how to create the adjacency matrix, but it's very easy with the statnet package. You just do as.sociomatrix of this bipartite network, and then the syntax. And if I just do this code before that last little bit, I'll get a large thing. I'll get, oh, no, actually, it's already fine. Never mind. It's already the right size. So this 1 to n.judges is sort of redundant, but cool. Okay, so I'm assuming now everyone's run this sc.projection equals the stuff. And so sc, if you do, just as a check, dim of sc.projection, it should be 14 by 14. So now I've projected this bipartite network into a unimodal network with 14 nodes. But it's still in adjacency matrix format. Okay?
It's also an adjacency format.
Oh yeah, so adjacency matrix, again, it's the matrix representation of the network. So if I have like a connection from judge 1 to judge 2 in my matrix, I'll have a 1 or other number in the spot 1, 2. So, right, so again, a connection from 1 to 2 would correspond to like A 1, 2 equals 1, or it could be another value if I'm doing a valued network.
So the adjacency matrix is just the matrix version of the network.
Exactly, yes. Okay. So there's a few little notes in there. Keeping with the big picture, I'm going to want to add some attributes to this network of judges. Not going to go into too much detail, but if you like, here, but it's all in the code. So just run this next block here. Okay. And lastly, if everything works, so let's try to just run this and then we'll see if anyone had problems. So SC, one second, sorry. So sc.unimode, sorry, it's hard to see, is net, but it's in the markdown. So it is network of sc.projection. So I'm using the network function. I'm giving it an adjacency matrix, which I created just now with that matrix multiplication we did, which I called sc.projection. Directed is false, right? So if 2 judges share a decision, there's an edge between them. It doesn't mean anything in this case for one judge to point to another or, in a direction. So directed is false. And then I also want to tell it, our adjacency matrix actually has values for the number of times 2 judges shared a decision. So I tell network to pay attention to that using this names.eval is false, which is kind of a weird command. I don't know why it's called that, but that's what it's called. And then I have this attribute list that I created, sc dot, with this other code over here. And I'm just going to feed that to the network so all those nodal attributes get pulled in. So if you run all the code in that chunk up to sc.unimode equals and then run that too, you should, fingers crossed, get something out like this. Okay. So where before we had a lot more edges, now we have a lot fewer, 73. And we have all these interesting vertex attributes too. So who's getting, let's be optimistic, who's getting this out when they type sc.unimode? Great, okay. Again, questions, Pamela, Arthur, Dan, but it actually seems like everyone's pretty much on the same page. So I want to now visualize again. Let's see what I have now, right? Probably, especially for a small network, the first thing to do is just look at it, see what it looks like. I create this other variable just so I can incorporate religion in my visualization. Again, so just run that, but we won't get into details of, of that code specifically. What I really want to show you is the plot that we can do now. Okay, actually, let's run it here. Okay, again, oops. Stop it. Why did you do that? There we go. Okay. So when I run all this plot code with the legends and everything, it's all in brackets. I should get out something that looks like this. People getting that? Okay. So compared to the last visualization that we did, this is a big step up because we can actually see what's going on now. Right, so we can see the judges. The color is if they were a Democratic or Republican appointment, so red or blue. And then the shape of the node, and network has kind of a weird way of making plot shapes, but we don't need to get into the details. But the shape says the religion of the justice. So we kind of just see like, oh, and also the size of, the relative size of these nodes tells me how many appearances they had in my data set. So like Kennedy and Thomas were on the most decisions in this time period, and Ginsburg as well. So we kind of see like the judges that appeared the most in our data are kind of towards the center. The ones that appeared less are kind of on the outside. Okay, so we're getting like some information, but we haven't even come close to answering the questions that we want to answer about when judges make similar decisions. Yeah, question? Yeah. Oh, that's just to scale it so that the nodes don't like take up the whole. Yeah, good question. Yeah. Yeah.
Going back a bit.
Yeah.
In sc.projection, that's a matrix, and the numbers. What are the numbers, the rows and the columns represent in that?
That's a great question. Let me address that question for everyone. So she's saying in sc.projection, what do all these numbers mean? Okay, so the off diagonal numbers, that's like Justice 1 and Justice 2 shared 11 decisions in my data. They made the same decision 11 times. The diagonals is the appearances. So Justice 1 appeared 19 times in my data. We ignore for the most part, when we're doing network analysis, we ignore the diagonal other than using it for, plotting and stuff. But generally, you don't really allow self edges. So that kind of gets automatically set to 0 when you're doing the analysis. But it's valuable to have, and it just comes naturally from how we projected this matrix. Yeah, good question. Okay. So right, so we kind of have a good visualization now where we can see who's connected. Oh, also the widths here, a little difficult to see, but they also correspond to how many decisions the two justices made together. And this is all in the code. You can see how I set these various things. It's fairly readable. You can see, what corresponds to edge width, vertex size.
But again, we haven't answered our question that we started with, which is what makes justices, do any of these factors tell us that justices are probably going to decide in similar ways, gender, religion, etc. So going back to, so we're over here. So why model? So one reason to use a network model as opposed to just a bunch of visualization and measuring a bunch of statistics is that these visualizations, there's sort of a limit on the number of things we can visualize at once, right? Versus we can model a whole bunch of characteristics at once. Another really important thing, probably one of the main takeaways that I want you all to have from this, if you don't remember anything else or how to code anything, a really important thing to remember with networks is that you use these default layouts to visualize a network, and they actually have a big impact, I think, in how we see the data. But then the algorithm isn't necessarily designed to show us what actually is there in the data. So like this default algorithm is for visualization. It wants to give us just the clearest picture with like minimal line crossings of our data. So it kind of tends more towards like evenly spacing than actually putting things close together that should be really close together. And again, that affects how we interpret the network. So we can use different, statnet doesn't have a ton of built-in layouts, but we can show a couple of the ones that it has and see like, okay, in this example, in this layout, it looks like now all the Democratic appointees are clustering together, where we didn't actually see that in this layout. So that's only a difference in how we chose to visualize it, and it has nothing to do really with the data itself, or it doesn't give us a systematic view of the data. So be careful with visualization and make sure that you have tried a few different layouts. There's also some randomness in some of these algorithms, which also can affect how you see it. And it's another reason why we'd want to use a model, right? Because models don't have this kind of ad hoc quality. Okay, so that's pretty much what I just talked about. Oh, and again, we want to analyze some factors while controlling for others. That's another reason to use a model, just in general. Okay, so we'll use this unimodal network that we've created to fit a model. So now we're dealing with kind of the ergom-specific part of this statnet world. So I added, partly just to show you how this works again, I added this birth year variable. So I said SC unimode %V% birth year is this data from before. It's just another way, if you forget a vertex attribute that you want to add, so you want to add it later, but you didn't put it into the network when you created it, this would be a way to add a vertex attribute later on. So let me run, so I guess you guys will run that. And then you run sc.ergom equals this thing. So what is this? So this is my first model that I've created so far. And it's saying I'm going to model my unimodal network as a function of the number of edges in the network, the number of edges where the gender of the judge on one end matches the gender of the judge on the other end. And similarly, I have node match. That's how you get this that quality, the node match term, right? It says how many edges match this judge's religion to this judge's religion. Same for who appointed or party that appointed them. Node covariate is basically, does the birth year systematically tell me something about how many edges each node has? So maybe I'll find that as the birth year gets later, that judges are less likely to have edges in the network because they just weren't on as many decisions because of when we took our data. This abs diff would say, is the difference in birth year between two judges important? Which it might be, right? Probably just, again, because of appearances, right? If a judge was born really early versus one that was born really late, probably didn't overlap very much. So they're less likely to have edges between them in our network. And then node factor of role, kind of similar to this nodal covariate, but for this categorical role. So role in our data, I didn't touch on it, but it's the, like if you're a chief justice. Okay, so I throw all these terms into the model, yeah.
Does the order matter?
Does not matter, yeah. All that matters is I have a network on one side, squiggle, and then all the terms I want to put in the model.
And then there's a whole bunch of other things I can set, but we won't talk about that at this moment. Okay, so I fit that. So let me just go over to the code, which keeps moving. Yes?
Does this model account for the fact that your data is non-independent? You have multiple measurements from a judge, and those aren't totally independent, right? Because the judges have personality and they're not going to vote randomly each time. My questions for you.
Well, so this particular model, you incorporate these covariates that I mentioned, so like things about the nodes especially. And in this particular model, that would tell me that given all that information, what happens on any individual edge is independent from what happens on any other edge. But I've incorporated the information about the judges, like, you know, religion and stuff like that. So it's sort of, there's independence given these covariates.
Okay.
Does that answer your question?
Yeah.
Okay. But the general question about independence of edges is an important one. It's not exactly your question, but it's important, and we'll come back to it a little later. Okay, so let me just run. Where did this code go? Okay. Oh. Okay. Okay. Good. And then so summary. Okay. So we should all be looking at this. So this is the summary of our model fit. So it's pretty similar if you've done a regression model in R. The general appearance of this is basically the same. So we have each of these things. So edges, I said this before, but I basically, unless you're conditioning a model on having a fixed number of edges, you almost always want to include an edges term. So it basically just like, it's almost like an intercept for a graph model. It's like, you know, nodes have a general underlying tendency to connect or not. It sort of like speaks to the density of the graph. Again, sort of almost you can think of it like an intercept. And then these other terms are more meaningful. You had a question?
Yeah, about the node match.
Yeah.
Is this any different from having a vector or binary vector saying the same religion or same gender? I guess I'm just trying to.
So node match only counts matches. You could also have like an edge attribute that says is an edge between different.
So it is kind of the same.
Similar. You could, and I don't remember the exact syntax, but I think you can also have like there's ways to control. I think there's ways to control node match where you actually want to count times when it's different and ways to modify it in that way. Yeah. Yeah.
Yes. I guess the question is, what is the probability of a network? What does it mean? Or
great question. Great question.
Our outcome variable? Why our y variable?
Yes, great question. Okay, so the question was, what does it even mean, the probability of a network? So when we do these models, we fix the number of nodes, okay? And unless we specify, which you can do in statnet, unless you specify, nothing else is really fixed. I mean, we know what kind of a network we're looking at. Is it directed or undirected? Is it binary or valued? But beyond that, we're basically just looking at the entire space of graphs of a certain size, right? And what our model does is tells us of all those cajillions of graphs, what's the probability of each one of them? And it tries to tune these parameters in the best way so that to match our observed network. But going back to, so the model specifies the probability of observing any given network in this enormous space of all the n by n networks or size n networks. Does that answer the question?
Yes, I think in addition, how many observations do we have here to?
That's another great question. So a big thing about network analysis in general is most of the time your n, little n, or sample size n is 1, right? In this case, right, we have one network of Supreme Court justices that they're basing our analysis on, right? Which is weird, right? Generally, we don't do analysis with a sample size of 1. Now, jumping ahead a little bit, what's a little surprising about this model is actually, at the end of the day, it's not really different from a logistic regression model. So because of the terms that I've included, there's actually no term in this model that makes one edge dependent on what happens on another edge. So, so I can basically treat, I could have run this like a logistic regression where I say whether an edge, if I, reducing this to the 0, 1 case for a second, I would say whether an edge exists or not depends on these characteristics of the nodes at its endpoints. But each edge, given all those characteristics, is completely independent. So it's like a logistic regression, probability 0, 1, depending on all these features, right? So in that way, actually, my sample size is like the number of possible edges. And so that makes this model a little more powerful. But it also means that I'm not really taking into account potential dependence between edges, which is kind of what makes network models unique in the first place. Yeah.
Question?
Yeah.
Sorry, but what should we be looking at? We're seeing this on the
Great, yes, that's what we're going to talk about next. So, so it's summarizing all these features that I put in the model. You know, kind of similar to a regression, like linear regression, are you kind of like, okay, well, what turned out to be significant? That's kind of what you look at first. So what this is saying is, again, it turns out this model is actually kind of like a logistic regression. We won't get into all the details about that, but basically, none of these node match terms turned out to be significant in this model. So basically, whether an edge exists doesn't really depend on all these features. They weren't important. The feature that really stands out is this abs diff birth year. So what I suspected before, that the birth year tells us it somewhat correlates to when these justices were in the court, right? We're serving. If the birth year is really different, then you just have fewer chances to overlap, right? You shared fewer decisions. So this coefficient is negative and significant because I think it's basically just capturing that, right? It's saying the further apart in age these two justices are, the less likely they are to share a decision. But really what it's saying is the less likely they are to even be making a decision at the same time. So this network, this model is sort of telling us that we need to do something a little better with our data, perhaps. So let me, let's see. So you'll notice the matrix representation of this is all 0, 1s. So we actually, we're treating this, let's see if I can see this anywhere. Okay, so yeah, I'll just ignore it. Basically, this model treated this network as a binary network, okay? And that means that anytime there was 2 judges shared at least one decision, there was an edge between them. So it didn't really distinguish between if judges shared a ton of decisions or just one. So that might be why we're only finding that this difference in birth year is significant, because we're losing some information about how many decisions 2 judges shared. Another thing to notice is, it's somewhere in the code, but I'll just type it out. Density, oh, here we go, it's right here. If you enter this, the density of this network is like 80%. So like 80% of the possible edges are there. That's actually really high for a social network in general. And again, that's because anytime 2 justices shared any decision, there's now an edge between them. So what should we do? Oh, and here they was just looking at the relationship between birth year and appearances in the data. So you can see, you know, the really old and the really young ones have fewer appearances in this data. Okay, so yeah, so we have this really high density that's maybe masking some important information that we want. So what we're going to do is, instead of just saying there's going to be an edge between two justices anytime they shared at least one decision, we'll make a cutoff. So they have to have a certain percentage of their decisions shared, roughly speaking. So that's what this next code does. So if you all enter that, you should get over to this histogram, which is here. So I'll wait a second, everyone getting there, running the code up to this point.
So the DIG, that's just saying they have to share that code equals 0.
Oh, yeah, that's just me zeroing out the diagonal because I don't want it to pay any attention. It's actually probably not even necessary. Oh no, sorry, for this it is necessary, but I just want to ignore what happens in the diagonal because that's like self edges. But basically, I'm creating a new version of the matrix where it's like, what percentage of my connections were to another person? And then this histogram looks at basically the distribution of percentages. So like the most common thing is that two judges aren't connected at all. And then here's like the percentage of their decisions that they share, the distribution. So there's no like obvious cutoff from this that tells me, okay, I should only connect two judges if they've had this percentage of their decisions together. So I was hoping to find that because this general idea of, okay, I have a binary network, it's not conveying all the information. So I'm going to install a cutoff for these binary edges. That's what we're doing now, saying, you know, I have to have at least this many decisions between two judges for there to be an edge. The choice of that cutoff is a little arbitrary, but it can really affect our output. So whenever possible, you want to have a meaningful cutoff there, or at least find some, you know, break in the data. I didn't really find that, so I think I just went with 0.1. And proceeded that way. But just a caution, it can have a lot of effects. So if you're not sure, try a few different cutoffs and make sure that the results aren't widely different. Okay, so all this code is basically just creating this sort of thinned out network. So if I had sc.unimode before with 73 edges, now I have this thin with 52 edges. So is everyone getting to this point where if you type in sc.unimode.thin, you see this thing, 14 nodes still, but 52 edges? If you've run all the code up to here, you should get that. Anyone having trouble? Raise your hand. Okay. Okay, so let's plot this again.
Excuse me, Jane.
Yeah.
Before you go on, I'm not sure. Can you pull the back see it? Because I can barely see it.
Oh, sorry. I think I made it smaller.
Okay.
Let me make it bigger again. Is that better? Sorry. Yeah.
Maybe another step. My prescription's
Yeah.
Okay. Yeah. Let me make this smaller. We're losing the console, but that's okay. Okay. So we thin this out. So let's plot it. It'll come down below. There we go. Okay. So you'll notice, even though I'm still using the default layout, so this is again plotting the thinned out network. Now I actually see a little more clustering in the Democratic appointees, which is kind of interesting. The edges are not weighted to anything in this visualization. Okay, and so let's see if now my model gives me something a little more interesting. So I run this this first one. I think I kept all the same features. I ran this. Let me go over to the output. Okay. Okay. So if you ran this sc.ergom.thin and then do the summary, now I see actually, so edges is significant, but that's sort of like in a regression model. Intercept is almost always significant. We ignore that. But religion now is an important factor in predicting when judges make similar decisions. Birth year is still important as well. And now let me take out the factors that weren't significant in this model. So I did that in the next one. So I removed gender, I removed role, and I ran it one more time. So my final model for now is that tells me that religion and birth year are important. Again, birth year still has to do with, you know, the opportunities judges had to make similar decisions. But it's interesting to me that religion, more even than, so the p-value for the party that appointed the justice, it's relatively small, but not nearly as small as religion. So in terms of at least First Amendment decisions, it seems like religion is a more important factor in determining similar decisions than even the party of the appointing president, which is kind of interesting and kind of unexpected. So I leave you from the modeling part of this with this quote about how judges are, you know, bipartisan, which of course they're not really, but maybe this is actually some evidence that principles, religion, history has more impact than party alliance. Yes.
Oh, sorry.
Oh, they're busy. Dan?
Oh, sorry.
Okay, so I promise we're almost done with this section, but it's always a good idea to evaluate the fit. So hold on, I left one. Let me just go over this code here. Actually, okay. So without getting into too much detail. So I just want to make sure, and this is partly because part of why this is so important goes back to the question before about, you know, what's the sample size? We only have one network. So we really want to make sure that simulations from the model look something like the observed network as a measure of the kind of model fit. So ergom, statnet more generally, has this GOF function, which is easy to just apply to this is the model output. And you can plot the result of that. And so it gives you a bunch of plots that compare this thick black line as observed statistics on a network compared to these box plots, which are simulations. And so it just gives you a few like factors of interest. So it always tells you like degree distribution. So this thick black line says, in my observed network, I had 0 nodes with degree 0, 1, 2, a few more. So it's sort of normalized, but a few more with degree 4. Most common is like degree 7 or 8. And it seems like, yeah, the simulated networks basically agree with that. And then it does the same thing for edgewise shared partners. So this is like sort of like triangles, but this would be, so this is, this means they have one, these two nodes have one edgewise shared partners. This would be that they have 2, 3, etc. So it's kind of like the number of triangles with a certain edge as a base. And it kind of describes clustering in a network, loosely. But you look at the distribution of that, like these triangle structures, that seems to match fairly well, yeah.
So I'm trying to like grab just an intuition of what the ERGM, the exponential random graph model, is doing. Because it sounds similar to a lot of things that probably many of us have had in statistics courses, but are you trying to maximize the entropy, and those are how you fit the parameters to these coefficients? Like what is the actual optimization that's taking place behind the scenes? What's the logic or the intuition behind the ERGM and how those variables are assigned their coefficients?
Yeah, so
there's this Monte Carlo space of like many possible realizations of these graphs that you could sample from, and then you could hypothesis test against how different is our observed graph from the many random graphs we can create. But how does that model fitting happen in the first place?
Okay, so without going into the details of like the MCMC, but ergom uses what it labels like MCMC MLE. So it's basically a maximum likelihood using a Monte Carlo based method, maximum likelihood estimate of the parameters. Okay. So parameters that make my observed graph most likely.
Okay.
Yeah. Cool. There's, I could say probably a ton more about that, but yeah. But actually, again, in this case, without dependence between edges, you can think of it as a logistic regression. That's actually what's being performed behind the scenes. Okay, so it goes through these kind of features of interest. It also compares geodesic distances. That's like how many steps from one node to another. That seems to match observed. Model statistics. So if the model actually fit correctly, so this is sort of a prerequisite. If the model fit correctly, the expected statistics from simulations from the model should match the observed statistics. So we do pretty much see that, right? So the observed is like towards the middle of these box plots of simulation. So that's a good check. So that's pretty much the default output of the GOF function, and you can tailor it to include other statistics or not include certain ones. But it'll give those three things: the edgewise shared partners, geodesic distances, and degree, are a pretty good survey of like, is this in general looking right? Okay. So I'm just gonna skip over a little bit of this. Another good check. Again, you can skip this code. You don't have to run it right now. It'll show you the output. Another good check is just make sure a simulation actually looks something like, because I might have missed something if I just look at graph statistics like degrees. So yeah, just a good sanity check is, does a simulation from my model look something like my observed? And you want to run a few different simulations, and yeah, it looks somewhat decently similar. There's randomness here, so if you keep running it, you'll get slightly different things. Okay. So, I think just, yeah, okay, cool. So the last thing I want to say about these models, and then we'll take a break and you'll have time to work on your own for a minute, is, okay, I had told you earlier that these models were hard to fit. You had to use MCMC, but when you run them, they actually fit basically instantaneously, as you've seen. And that's because, like I mentioned before, all the terms don't imply any dependence between the edges. So it's called a dyad independent model. And that means I can treat edges like these independent draws and run basically a logistic regression to fit the parameters. So I could also force ergom to use its MCMC tools for estimation. By doing control dot this code here, control.ergom forcing MCMC. If you wanted to say like include a sample easily, but a more likely thing for you to do is actually include a term in the model that violates dyad independence. So without going into detail about what this is, this GW degree term is a relatively non-degenerate measure of clustering as measured by degree distribution. So the number of nodes with degrees, 1, 2, 3, et cetera, certain degrees. It's sort of like an aggregate measure of that statistic. Again, I don't want to get lost in the details of this, but the important thing for us now is that it is it induces dyad dependence. And so ergom will automatically run its MCMC routine. And when we do that, we want to make sure that the MCMC is good. So in addition to doing a summary of the model, we'll plot it, and that will automatically print these diagnostics. So I don't really have time to go into like MCMC diagnostics and what they are and all of that, but just know that ergom has this built-in capability to run diagnostics on its own models. They should look something like this. It's kind of like randomly distributed trace plots. So it's sort of like tracking what the samples did over time. The density of your parameter estimates should also look like, somewhat symmetric, have, generally unimodal, if everything's running correctly. And then I ran the same goodness of fit on the model with that GW degree term. Everything still looks pretty good. Not really gonna, you can take some time on your own to look at the difference with and without that term. I think we have sort of bigger things to do with our time, but yeah, you can compare that output. And again, you could compare simulated to true from this new model that had that GW degree term. They look even slightly more similar, but I can't say if that's just due to randomness or if the model is actually doing a better job at this point. Yeah, again, I'm going through this kind of quickly because I just think we should get on to the next section. But all this code is here and explained. If you want to see a model really fail, add a triangles term to it, and it will probably explode. and give you an error. And that's generacy in action. Okay, so let's take a break now. I gave you some things to try. I think you could also just relax for a second. But there is, so this ZAC data, if you do want to try this out in the repository, in the data, there's this ZAC data, so you can load that and play around with it. It's this famous network, the Zachary Karate Club network. Yeah. All right. Yeah, 10 minutes to get. And if you have questions, I'll be around now to answer them. Any last questions before we get back to it? All right, let's do it. Okay, so so that was the end of the statnet tour for now. Still just the tip of the iceberg, but time is limited. So we will move on to the igraph package. So the statnet package kind of has its roots in like real human social networks. Authors are a mix of like statisticians, sociologists. The igraph package kind of comes more from like an applied math, physics, what else? Yeah, computer science background. So it's less geared, not entirely not, but less geared to modeling and more geared to things like community detection, which we'll look at, calculating statistics on a graph. And it's generally a little more designed with large networks in mind, like, you know, hundreds of, it can handle in some cases hundreds of thousands of nodes in some cases. Yeah, but it's so I know it's a little tough for me to kind of like throw an ergom at you, like just put up an equation and then expect you to use it. It's not really enough time to fully grasp it. Thankfully, in this section, we're not really going to deal with network models. We're dealing more with algorithms, things we can use to describe graphs. So yeah, igraph, tons of descriptive statistics, community detection algorithms. So if you're not looking for a modeling framework and you just want to like do graph statistics and community detection and stuff like that, igraph is probably where you want to start. We'll get to that. It has a Python version. So if R is not familiar to you, it's also good. And yeah, then it, you know, it's sort of in this general ecosystem of packages. Okay, so let's just jump right into an example. So in the repository, I put this data, this cross citation matrix.csv, and we'll load that in the code. But what this is a network of statistics journals. And the data is the number of citations from one journal to the other. So not going paper by paper, but the whole journal over a, I forgot, 5 or 10 year period, I think. And it comes from the certain paper, which I have linked. And so with this network, so unlike in our previous Supreme Court justice case where each node had a lot of features, you know, like the judge's religion and age and stuff like that, now the nodes don't really have a ton of information. It's just the journal. And we really care about analyzing these citation counts between them. So we'll also be interested in potentially like visualizing the network, which journals seem most important or most central in this network. Are there sub-communities of journals, and maybe other network features. So again, getting away from kind of the modeling framework and looking more at these kind of algorithmic descriptions of the network. So we need to load our new data. Hopefully it'll be a little easier this time. So we'll run this code, which is now, where are we? Line roughly 500. So you just run that code and you should end up, it's creating So similar to before, we kind of started with an adjacency matrix, although we didn't have to do as much to it. We'll do a couple things, and then we'll actually create 4 different versions of this network. So the igraph function is this graph from adjacency matrix. You actually specify like that this is an adjacency matrix I'm starting with, not an edge list or something else. I'm telling it in the first 2 cases that I want a directed graph. And in the first, so this is the graph we're going to use most often, or the network we're going to use most often in the rest of this section. It's the directed and weighted version of the network. So just C graph or like citation graph is what I saved it as. But we'll also create a binary version. So I say weighted. By saying that weighted is equal to citations as opposed to true, it actually just creates an edge variable of the citation counts. So like each edge, you know, has connected with it the number of citations from one journal to another, but it's not treating the graph as weighted. So the edges are still 0, 1 in that case. And then I create 2 more where I have it as undirected instead of directed. So the edge would be like, is there any connection between these 2 journals? Same from I to J as J to I when I have these symmetric versions. And I just create them all now because I'm going to use them all probably at some point later. So I'll just do it all now. See how that code works. So, and if I look at it, it looks different than a network from statnet, right? When I print out what that network has, it gives me this kind of information where it's like, okay, 47, that's the number of journals, number of edges, different the attributes that it has, and it starts listing out the edges. So it's a little bit less of like an easy to read summary. Okay, we can look at some things. I'll go back over here. Right, if we did this all right, we can look at like density of the graphs. Of course, the symmetric or undirected graph is going to have a higher density because all I need is like 1 directed edge between any 2 journals for there to be an edge ultimately. Make sure that I got the weighted stuff correct, so you can check if the graph is weighted or not. Then you can also extract that. If you want to just look at what the weights are, you would extract it. Now, notice here, this is going to be really important when you hit an, I'm sure at least one person will hit an error later, where the cause is because a function in igraph has the same name as a function in statnet. And so it's not sure which one to use and it hits an error. So if that ever happens, the first thing to try is just put this igraph prefix on if you know you want to use the igraph version. So then it knows, okay, give me the version in igraph. Okay, so we've loaded our networks. Anyone having problems loading networks this time? Great. Okay, so we want to visualize them. It's usually our first step. igraph, like I said, has a lot more layout options. It's definitely more geared to that than statnet. And so below, we just compare running all this code. You don't really need to do it, but compare out from a bunch of different layouts. And I don't even think this is all of them that you can use in igraph. So grids, circles, stars look a lot like circles, other stuff. And again, it's really important to recognize that the visualization layout algorithm is going to affect how I see the data. Okay. And another thing to note is this code here, you can set the layout. So if I know I want nodes to be in certain positions, which is really useful when you're like doing a bunch of different analyses and you want to keep the same layout throughout, you can set the graph layout this way. And then you can also extract the layout. So like, if I laid out this C graph with the grid, this code makes L actually, so let me just run that and show you better than explaining it. So if I set the graph attribute of layout to be this certain layout, then when I plot it, it'll keep that layout. And then I can take this, right? This L now is actually telling me where to position things. So because it's a grid, it's all these like, you know, neat positions. But I could do something a little more Sure, there. Now it's going to give me some, you know, three-dimensional positions. But let's go back. But yeah, you can extract the layout from a given igraph and use it later. Whoa, what just happened? Okay, yeah. So now when I plot cgraph with this layout L, which was just, you know, where the things are supposed to be laid out, this custom layout L, it looks like this because L came from a grid, but it seems trivial, but actually it's really important, and a lot of like Stack Overflow questions about igraph visualization are basically answered by just putting in a custom layout. Okay. And of course you can change colors, vertex sizes, all that stuff, the same stuff you can do in statnet. So this is just an example of that. So this is definitely prettier than the plots above. But what I don't like about it is that all this overlap between the more central nodes. So I'm not going to go a ton into the ggraph package or the ggplot kind of family of packages. So actually, who here uses like ggplot regularly? Okay, so a lot of people. So there are network visualization tools within the kind of like ggplot family. Not going to go a ton into them, like I said, but I do want to highlight one thing that's really useful, which would have saved me a lot of time several years ago. You can use this, the ggraph package. Again, since we're short on time, I'm just kind of go through what this is and not actually run through the code. But you can plot this, this igraph object in ggraph with a certain layout, right? So this is like kind of the basic code. And then you can set a bunch of things, but the really important thing is to set repel is true. So that uses the grepel package. And what that does is now I can actually see. It's really the same layout as before, but I can actually see what's going on because the labels are placed where they don't overlap. So just wanted to make you aware that this is available because I think it's really useful at times. That's all I'm going to say about the ggraph package, although I did want to make one more clarifying point. So if you're like, okay, I use ggplot and there must be some kind of like visNetwork stuff, right? What is it? So you go and Google it and you find a whole bunch of stuff. So there's ggraph, ggnet, ggnet2, and visNetwork. And you see all that. I'm not sure which one would come up first on Google, but you see all that and you're like, which one should I use, right? And actually, I wasn't even sure of what's what until I was writing up these notes. And it turns out, so ggnet2 is basically just an improved ggnet. visNetwork is basically defunct at this point. So these two, ggnet and ggnet2, have actually been pulled into this ggalley package. But they do some basic GG type network plotting. visNetwork, so this is from the author of visNetwork writing to the author of ggraph. This quote here, where he says, it seems we have coded more or less the same thing, but your project goes further than mine. So he's basically like, I'm going to forget my project, yours is better. So long story short, use ggraph because it's going to be actively maintained and it does everything all these other ones do. And that's pretty much all I wanted to say about visNetwork visualization. Okay, so now we've plotted our journal network in a few different ways. So now let's start answering questions that we want to know about it. So our first question is, which journals are most important? This is the kind of question that statisticians love to think about in their navel-gazing ways. And there's a lot of different answers depending on how you interpret the question. So the first thing to note is like importance and centrality are very overlapping characteristics of things in a network, but they're not the same, right? In some cases, we mean them kind of the same. For if a network is really central, it's kind of like this clearinghouse of information. Maybe to us, that also means that it's important. But there might be other ways to define importance. For example, if you're looking at transportation networks, a node or a station that tons of stuff is going through, we might consider that the most important. And then we'd be looking at something more like it's like betweenness centrality. So does a ton of stuff go through this node, putting it, you know, very roughly. Okay, so I just listed out a few different kinds of centrality that we might be interested in. Not going to go into detail about exactly how all of them are calculated. I mean, the names kind of give it away, right? So degree centrality is basically what's your degree, or what's your kind of like weighted value if it's a weighted network. How much stuff is going either in or out from the node, or a total, depending on your purposes. Between centrality, I kind of already mentioned, like how much stuff is flowing through a node. Closest centrality is like how many steps does it take to get from that node to other nodes. So if those paths are generally short, you know, if that means high closeness centrality of that node. So you can think about it in the journal case, right? If a journal has really important papers, then almost every other journal is going to cite that journal directly. So the closest would be low, right? The number of steps I have to take to get back to that main journal is small, right? So that could kind of indicate importance of a journal in that case. Eigenvector centrality, again, don't really have time to get into exactly the calculation formulas here. Okay, so I kind of already gave it away, but in a network class that I took, the professor once asked, what's the most well-known algorithm for determining importance of nodes in a network? Does anyone have a guess? Yeah, there you go. So I, being like a network scientist or whatever, I was like, well, degree centrality, right? Because it's just the degree of the node. That's the, and the professor's like, no, it's PageRank, right? PageRank being the algorithm, the basic algorithm that spawned Google's search engine, is indeed probably the best known algorithm. And it's interesting that we're applying it now to journals because it actually has root, like both eigenvector centrality and then PageRank, which is basically a variation of eigenvector centrality, have roots actually in journal networks and trying to figure out what's important in a network of journals. Okay, so again, don't really have time to go into the details, but PageRank, I guess one just important thing to point out is with both PageRank and eigenvector centrality look at the importance of the nodes that, so say I have like, you know, an important web page. If that web page is linked to by a bunch of other important web pages, that probably means that it's important too. And the main difference between so both eigenvector centrality and PageRank take that into account, but PageRank also takes into account, if I have this page here, if I have this page here and I think maybe it's important and it's pointed to by this other important page, PageRank also cares how many pages this important page points to. So if it points to a ton, then the fact that it points to this one doesn't mean as much as if it was only pointing to that one. Okay. Okay, so and these are all centrality measures that are easily implementable in igraph. And there's many others, including some that are in igraph and just many others beyond igraph. But so the next code just goes through the implementation. It's all pretty straightforward. One thing to note is if you choose a degree of this cgraph, which is our network of journals, it'll actually give you the degree as if it were binary edges. If what you want is like total citations to or from a journal, you want to use the strength function and specify the mode as in, out, or total for in degree, out degree, or in strength, out strength. Yeah, then we go through betweenness, just the function just estimate betweenness of the graph, closeness, eigenvector, et cetera. It's all pretty similar code. These plots, I'm not going to go through them right now, but I plotted just relationships between degree or strength and these different metrics, et cetera. So, and there's Sir Jabrin asking us how to choose now. So we've calculated all these different centrality measures, and then actually I added one more in that's kind of, instead of the degree, it's almost like a normalized degree. So it looks at the ratio of citations in to a journal over the number it sends out. So it kind of normalizes for like journal length, right? A journal that's really long, and other things, but a journal that's really long will have a lot of in citations just because it has more articles. So I can kind of control for that by dividing by the number of citations that it sends out. And if the number of citations that come in is a lot higher than the number that go out, it'll have a high number, maybe indicating importance. Okay, so summary. So you ran all that code, and then now this plot compares what are the, let me make it a little bigger. What are the resulting ranks of each journal from these different algorithms? So sometimes they're pretty similar. So here's an example, like BioJ, forgot what that stands for. One of the biology or biological statistics journals. Looks like it's kind of similar across the board, but others can vary a lot. So for example, the Journal of the Royal Statistical Society Series B, which is like their theoretical journal, it's generally ranked very highly except by betweenness. So, and that might be because it's kind of at the top of the game, right? So not a lot of things go through it, kind of more like everything just points to it. But yeah, you can look through these, and so these red rows are highlighted because there's a general loose consensus of these 4 journals as like the top 4 statistics journals. So if we're doing a rank of importance, we'd probably want these 4 to be at or near the top. So you can just kind of check which algorithms do in fact produce that. And most of them do. Total degree actually has CSDA and, well, JASA, and also, or the, here, statnet. So I think it's statistics in medicine ranks really highly on a degree measure because there's a ton of citations going into it, but there's also a ton of citations going out of it. Just kind of a prolific journal. But if we're looking at importance, we kind of want to control in some way for the number of out citations, or favor the number of in citations, right? Because really important articles just have a ton of citations coming into them. Any questions about this? Like I said, I didn't actually go through step by step on the code, but it's fairly straightforward to follow, I think. And I really just wanted to get to like, okay, there's a lot of different available centrality measures in igraph, and they're all slightly different. And actually, this data was sort of culled to have somewhat homogeneous patterns between the journals. So it actually kind of hides a little bit some of the differences between these measures. They would come out more if there was massively heterogeneous connection patterns between the items in the network. Let's see, what else did I want to say? Yeah, so between the centrality and total degree, tended to favor just journals that have just a ton of in and out citations. And so they're slightly different than the other metrics. And yeah, this is just a small sample. So I also wanted to just mention this other package. I haven't really used it in practice, but it seems kind of cool. So this CINA package, and again, I can just go through this. You don't need to play along. It will actually tell you just a ton of available centralities that you can calculate on a certain graph coming from all different packages. So like there's 51 available for our network of journals. And then you can just kind of calculate as many of them as you want. So here I just specified, give me the first 5, but you can give, all of them a subset depending on your interests, and it'll just run it all at once. So you don't have to go, looking for all these different packages and all these different measures. So that's kind of useful. But the downside of it is you can't necessarily put in all the arguments that you could if you called the centrality measure directly from the package that it's from. So if you really need to customize, you probably do have to go like straight to igraph or whatever the package is. Okay. Next question. Are there sub-communities of journals? So even though we're in just the world of statistics journals, maybe there's kind of like subfields within there that we can identify. And so this brings us to this more general question of community detection or graph partitioning. So they're similar tasks, but slightly different. So graph partitioning is generally, give me the cut of the graph where I cut the fewest edges. So let's just assume I'm cutting it into 2 groups. I might also, let's see, let's ignore. Okay, so yeah, cutting it where I minimize the number or the weight of the cut. Community detection is kind of more generally defined as where are the natural fault lines in this graph, and what exactly that means will depend on the metric that you're using to come up with your communities. So this is how the cut size is defined if you're doing this graph partitioning thing. You can implement a minimum cut in igraph with just min cut to minimize the cut size. Now the problem is you can't specify the size of the groups that you want in that function. And so when I run that on our network of journals, it gives me back that the best cut you can do is to put this one journal in one group and then all the others in the other group. Because that's the best, right? There's just the one connection with that journal, or a few connections with that journal. I just have to cut, and now I've created 2 groups, but that's not actually helpful at all. So another thing you can do, so these graph partitions, without being able to specify the size, might not be so useful. Another method, which as far as I know isn't directly implemented in igraph, but just a few extra lines of code can get you there, is the spectral partitioning method. So there's a little bit of explanation here. I'm not going to go into super detail, again, not really time, but you can see so you can kind of get the tools you need for it in igraph and then calculate it without too much extra work. Do you have a question?
No.
Oh, sorry. And then, so what that will allow you to do is actually set the size of the 2 groups in your cut. So this plot just compares so it's actually, so I haven't explained what modularity is, I will very shortly, but it compares the modularity resulting from the different optimal cuts as determined by this spectral algorithm. And then so red line would be just like a random cut. If I just partition the graph randomly into these 2 specified sizes, what's the modularity, again, to be explained, what's the modularity of the output? Random, it kind of just fluctuates. Maybe it dips a little bit when I have more equal group sizes. But you can see for the spectral partitioning, we kind of have a steady increase. We find a relatively high modularity at around this size. So I included a kind of reflection. You can ignore it. The important thing is to see, okay, as I change the group sizes, I get more modularity and then kind of less. So we'll save this maximum. We're going to save it as this gp.spectral membership, and we'll use it later. But so just remember that this was the sort of the best cut of our graph using this spectral graph partitioning, where again my goal is minimizing cut size between 2 groups. And then I can plot. So use that output, the best graph cut, I can visualize it. So one group resulting from that is in green, the other is in blue, and this is what it looks like in a basic visualization. Okay, so the simple example I gave with min cut, it said, okay, the best way to cut is just take out this one node and put it in its own group. And that kind of speaks to a larger feature of graph partitioning, which is it looks for the best cuts in terms of the size, right? It wants to cut the fewest edges. What it doesn't take into account is what those edges are expected to be. So if I have a bunch of nodes with really high connectivity and high degree, and a bunch with really low connectivity and low degree, it'll probably just cut off the low connectivity edges, right? Because that's where the small edges, the small cuts are. But that's not really that helpful, unless that's what I'm looking for. That's just going to give me one section of high degree and one of low degree. But when I'm doing community detection, I kind of want to know, relative to some expectation, which edges are more likely to be connected and which aren't. Is there some feature of the nodes? So like, what subfield of journals they're in that says, okay, this subcommunity has a lot of edges in between it, but relatively few kind of on its exterior. And maybe that's where I want to divide my communities. But if I'm looking at 2 high degree nodes, they're going to have probably a heavier edge in between them
just because they're very connected. But if that edge is lower than you would have otherwise expected, because maybe one is the biological subfield and one is computational, then maybe I'd want to cut my community there. So that, in a very broad nutshell, is what modularity, which I mentioned earlier, does. It's saying, give me communities with higher than expected connectivity within them and lower than expected connectivity where I kind of cut them up. And that's just formalized in this metric. Okay, and then actually finding the optimal communities in a graph, or maybe plural, is kind of hard. You have to look at a whole bunch of different options. It's slow. So igraph implements these kind of approximate but pretty good algorithms for finding or almost finding the community splits with at or near maximum modularity. So there's 3 that I mentioned here in igraph: the cluster Louvain, cluster fast greedy, cluster leading eigen. They sound all different, but they're actually just different ways of maximizing modularity in your communities. So yeah, that's kind of like modularity maximization is one broad school of community detection that you might want to use. Yeah.
Isn't it different from traditional clustering, like K-means clustering?
Yeah, they're just optimizing different things. Yeah.
Kind of related to his question, like, how is there a way to get an idea of how many communities are just good where you just have to try stuff and see what looks good?
Good question. So modularity maximization, you don't have to set the number of communities when you run it. Let's just go back to this code here. So yeah, this is actually the code to run these different clustering or community detection algorithms. You're just giving it the graph. So I'm using, I'll come back to actually a second. Okay, so just give it the graph and the weights in the graph, and then it returns. But again, you're not putting in the number of communities in that function. So now's a good time to mention that when I do these clustering algorithms, I'm generally using the symmetric version of the graph. And part of that is just implementation, what's available in these functions. But it also, if you think about community detection in general, though not always, community membership is a symmetric quality, right? If I'm in a community with you, you're in a community with me. So it kind of makes sense to think about the symmetric version of the graph, because again, community detection itself is like symmetric in that way. That's not to say that there aren't, so we don't have time to talk about block models. That would potentially be one way to incorporate directed communities in a meaningful way. But just so broadly speaking, community membership, it kind of makes sense to think about it for symmetric graphs or undirected graphs as opposed to directed. And so for consistency, all these metrics I'm using on the undirected graph. Okay, so I apply all these different metrics. Again, pretty easy. It's like cluster Louvain is the function. I just give it the graph and I give it the weights. And then I get the resulting memberships from all these different algorithms. And I'm also going to calculate the modularity based on these clusters. Okay, and now let's visualize what we get. Oh, sorry. One more kind of general approach to community detection, these random walk methods. So instead of trying to calculate this modularity or some other function over the whole graph, I might want to just start a random walker at some point in the graph and see where they go. And the idea generally, for all these kinds of metrics, if there's strong community within the graph, then this walker will kind of tend to stay in that community, right? Versus everything's kind of spread out, they'll kind of traverse the whole thing, right? So that's the basic idea behind them. And what's nice is that when I do that and I look at just this random walker at this place and going a certain length, I don't have to calculate something on the whole graph. So if the graph is enormous, it can save computation time. And in some cases, it would be
you know, one of the only kinds of approaches you'd even be able to use. So that's just another kind of general school. Again, I mentioned block models, but don't really have time to talk about it. And it's also not really, a few block model things are implemented in igraph, but the basic model is not there. So I'm leaving it out. But yeah, so we have this cluster info map and cluster walk trap are two random walk type metrics. So now let's compare. These are plots, again, basic layout, plots of the results of community detection from the different algorithms. And then this is the modularity that we found. So this Louvain had the highest modularity of any of the algorithms that we tried. Our spectral graph partition, so again, that minimum cut divide has the lowest, which kind of makes sense because it's optimizing something that's not modularity. And we also see the number of communities returned is different, right? So these modularity maximization algorithms all return 3 somewhat similar communities, but InfoMap actually just finds one community, everything's in one community, which says, you know, there aren't these, if you had a random walker, it would kind of walk all over, it wouldn't stay really tightly in one spot. Walk trap finds 2, but still finding less than modularity. And spectral graph, we only allowed it to find 2, so it found 2. But yeah, again, the metric that you use to calculate community is obviously going to affect the output. So do not run this code unless you've installed igraph from source, which why would you have done that? But this function cluster optimal actually finds the optimal relative to modularity communities. So I just wanted to compare it. And actually, in this case, the Louvain algorithm gets the same modularity. I think it even returns the same clusters. So yeah, it's been phased out for software reasons, but if you really want to find the optimal modularity, install igraph from source, and it's there. Any questions about those community detection things? Okay, so lastly for igraph, like I said, there's a ton of other graph statistics that igraph can calculate for you. I'm just going to mention a couple. Reciprocity. So for journals, right, I might want to know if I'm citing one journal, is it also citing me in return? Or do I have more of a hierarchical relationship? So the reciprocity, and that's what reciprocity measures, the reciprocity in igraph will treat it like a binary network, which is probably not really what we want in this case. So you can actually just use like a basic correlation. What's the correlation between, let's see. Oh. Is this what I wanted? Actually, that might be wrong. I'll have to think about that for a second. But the idea is the same. Can I find the correlation between from I to J and J to I? No, yeah, I think that's right. Right? Yeah, okay, because I took the transpose. Yeah, okay. So this is basically measuring correlate. If I look at edges from I to J, J to I, what's the correlation? Right? If there's a lot of reciprocity, that correlation will be really high, close to 1. Okay, another feature, assortativity. So there's 2 different ways to think about assortativity. But it's basically the same thing. By degree, that's basically do high degree nodes connect to other high degree nodes, or by characteristic, right? So like in our Supreme Court justice example, do nodes of the same gender tend to connect to nodes of the same gender or not? So assortativity is just a measure of that. And then clustering coefficient or transitivity, it's not super relevant to our examples, I would say, but it could be for some of you in your work. So the idea is, if I look at a node and then I look at all its adjacent vertices, so this is my main node, right? If this node doesn't have high clustering or transitivity, then these nodes won't really be connected. But if it has high transitivity, then all of its friends are friends. Right? And so you'll see kind of clusters around that node. So that's the basic idea of what that calculates. And again, igraph just assumes you're using a binary network when you feed it in. Okay, and then let's see. I was going to give you something to try out igraph. Who wants to try out some things in igraph and run some of this code on your own? Or who wants to just keep going? So who wants to try things on their own? Raise your hand. Who wants to just keep going? Okay, we'll keep going. Okay, I think it's all pretty straightforward, especially with these examples that I've given you. but yeah, this is a small subset of the things that igraph can do. So I encourage you to explore. And the documentation is there, so you can see like the full, actually have it up, the full list of all the various functions available in igraph. It's quite a lot. Yeah, actually also another thing to note is a lot of functions in igraph have kind of like aliases. So the same function will have two names, something to be aware of. Sometimes a period is replaced with an underscore, who knows why. Okay, moving right along. So we don't have so much time. So let me ask you, since we might run out of time. So we could go to another kind of modeling framework, which I really like and think is really valuable and interesting, but it is another modeling framework, so there's kind of a learning curve in just what this model is. Or we could go to a package with kind of a built-in dynamic visualization, which just makes it really easy to create an interactive graph visualization. So if you want to do the model, raise your hand. If you want to do the interactive visualization. All right, well then we'll just go in order. Okay, so another package, not as nearly as prominent as statnet or igraph, is this latentnet package, and it's kind of related, at least in the authors and some of the code, to the statnet family, but the model itself is very different. So latentnet implements these latent space models of networks. So what they do is they say, okay, I have my vertices. I'm going to pretend that they live in this unobserved social, potentially, space. And then I'm going to say that the probability or the weight of the edges between them decreases with their distance. So if they're further away in the social space, they're less likely to be connected, or they'll be connected at a lower strength.
When you say distance, you mean distance in social network?
In the social space, so which we'll have to kind of estimate where they live in the social space. So what's really nice about these, a couple of really nice things about these models. One is that they don't have the degeneracy of ergoms, partly because there's more parameters, so you kind of have a more complete description of this space. And more formally, it's once you've kind of fixed them in this space, there's more independence, so it's a lot easier to estimate things. Another really nice thing is that when you produce a visualization from a latent space model, it's model-based. So you're no longer just making these ad hoc decisions in how you lay out the nodes. They're actually based on what's the best positioning in my model based on my data. Yeah, ignore that last point. Okay, so this is just an example of a latent space network model. It doesn't have to be Poisson. So Poisson is used here because I'm gonna apply it to the journals where the edges are valued. But this could also be like a Bernoulli or something. But it's kind of, if you've seen like generalized linear modeling, it's that basic framework, right? Where I have this kind of like sort of regression-y looking thing on the inside, and then I convert that to the scale that I need. So this thing, which is in negative infinity to infinity, ends up on like a positive, being a positive, and then it's the expected value of a Poisson distribution. So what this says is the expected, one thing it says is the expected value of edge from node I to node J would be this value here. Okay, and so so where this is kind of like an intercept, this is like a bunch of covariates and their coefficients, and then this last part is the distance from node I to node J. So again, the farther away they are, the lower this value goes, and then that drives Yij down as well. Zi and Zj, so those are the positions that I have to estimate of where these nodes live in this unobserved social space. So all these things have to be estimated to fit the model. So given, and this is where we kind of avoid degeneracy, given all these parameters, what happens on each edge is independent. So given where I've laid out these people in social space and everything else, I can look at these edges independently, and that makes everything else a lot easier. Okay. that's the basic idea of the model. Here's some notes about everything up there, but I'll kind of skip over them and apply it. Okay, so now if you've loaded the LatenNet package, instead of so this is where you kind of see connections between LatenNet and statnet, even though the model is very different. But instead of using ERGMM, the model is instead of using ERGM, the model is ERGMM to fit the latent space model, extra M, very important. I've already in the code converted my journal network to a statnet type network object, which I feed in to the model. And so with this, so now this is the code, just stepping back for a second. This is the code to fit a latent space network model to this valued journal data. And I put in, so this first term says, it's just Euclidean d equals 2, says this social space exists in 2 dimensions. But I can specify it to be 3, 4 more dimensions if I want. Generally, people use 2 or 3 for visualization. Our sender is a random effect for each node, which says, which captures like its tendency to cite outward, to send out citations. Our receiver is the opposite. And then I tell it, I want you to incorporate those citation weights in this model, and we're using the Poisson for these valued weights. And here, for time, I have it fit with an MLE. So LatenNet, like statnet, will use a full MCMC estimation method, unless you tell it otherwise, or unless it has reason not to. And that's because the likelihood function is not convex. It's not because of something else. But yeah, so I can force it to fit with this kind of fast non-MCMC method by saying toFit is MLE. And then it will run really quickly. But what I would recommend you doing is you can either leave this blank or specify some things that you want it to do when it fits. But if you leave this blank, it will automatically go to its MCMC. And then not only do you get out the estimates of the model parameters, you get with it kind of like a sample from the model, basically, which you can use to calculate other things about it. So because it's an MCMC, you'll also have to specify or use default values for like burn-in interval. Again, I won't go into MCMC details, but for those of you who've used that technique before, right, this will be familiar to you. So you fit the model. So again, this takes a few minutes to fit, so I don't recommend you doing it now. The output is actually saved in the repository. If you go into output, this thing, RDS, you could load that. I even say in the code how to do that. And then that will give you my output when I fit this model with all this burn-in and everything. Okay. And yeah, so I mentioned here it's where that model is stored if you want to look at it later without having to run this code or even without having to load the data. Okay, so we run this model. We want to inspect the output. Because we're using MCMC, we should always look at the MCMC diagnostics, which you could do with this code, but we won't inspect them right now. And then we can plot it. So this is all just kind of like settings on the plot. This first thing will give us just a basic plot of where the journals now are estimated to live. This next thing actually, like I said, because we're using MCMC to fit it, it comes with a sample that we use to get our estimates. And we can use that sample to get an idea of the uncertainty in our estimates, which is always a good idea. And another reason to use models in the first place. You don't just get estimates, you get some better understanding of how confident you are. So what we'll do is we'll use that sample, this code to use that sample to then plot all the kind of different places where these nodes could live. So let me just show you, shut up and show you what this looks like. So these are the model-based positions of the, I know this text is kind of small, but model-based positions of the journals in the network. So like, oh, and these sizes kind of depend on those random sender and receiver terms. So that's how this is how we calculated the node size. So basically, like if a node tends to receive a lot more than it sends, it's big. So it gets a lot more citations than it gives out. These groupings, which you haven't seen before, actually come from the paper where I got this data. They use a different clustering algorithm, and then they kind of applied what they thought were the appropriate labels to the clusters after the fact. And so I just wanted to color, partly just wanted to color the nodes by these labels and these clusters, so that when I do the uncertainty, you can really see, right? So let me see if I can get these into one. Yeah, okay. So you can see like this one red node, maybe you can't see the color from back there, but there's this one node over here that kind of like occupies all these kind of spaces in the sample. So it's tempting to be like, these are the positions, but just remember there's uncertainty here, right? It could be in just this run of the estimation, they could kind of hover in any of these clouds. Okay, and then lastly, I wanted to show you one of the reasons why I like model-based visualization so much. So I took the Louvain modularity maximization partition from before, and I plotted the network where nodes are positioned with their estimated latent space model positions, but I colored them using the modularity-based communities. And I think it's a lot clearer now that how those communities actually exist in our model, right? It's much clearer, oh, that's actually like a meaningful community. And I can see, not only can I see that that's community, but I can see how the community itself relates, right? Like I know within this community, BioJ and LDA, and you can't read those, but that's what those two nodes are probably less connected, right? Because they're further apart. And I can make meaningful statements about connectivity in the graph just from the visualization, which I couldn't do when my layout was just give me a even spacing.
Can you remind us what the size of each node is?
Yeah, so the larger the node is, that means that its random receiver estimated value was high, so it takes a lot in, and it's relative to that, its sender value was low. So it's like taking in more citations than it's giving out. So, and then you can't see this either, but Journal of Royal Statistical Society Series B, the theoretical of their series, has the largest node, and you might then say it's kind of the most important journal based on this data.
So this we were talking about with the Supreme Court justices, it was bidirectional. This is not that. It's directional matters.
Exactly. Yeah. So the data, the graph is directed. The positions, now this is important. The way that distance in social space figures into the model, that's symmetric, right? You fit these positions, and then the distance from I to J is the same as the distance from J to I. But the random sender and receiver values in the model kind of get to more of the directed effects of what's going on. Okay, and then I'll just show you. So there's another package called visNetwork, which was the first package I used to create a dynamic visualization of a network in R. So these plots, I really like these plots for all the reasons that I've said, but they're still kind of cluttered, right? So dynamic visualization can really help in kind of decluttering and helping you focus on certain things. So this is the code I'll use to produce a dynamic visualization, and I will just show you what the output would look like. Okay, so it's not that much code. I mean, it's not that much more than, where to put it? It's not that much more than you use just in basic, basic plotting and setting all the colors and everything. But you get out this really nice interactive thing. So I can see, I can like go to a certain journal, it'll highlight it. I can see all the connections. I thinned out the edges a little bit just for the visualization here, just again to kind of declutter, but you can see everything that's pointing to it. You can click out, see everything that's pointing. Oh, wait. There you go. Okay. So kind of see what's connected to that, and you can just play around with it. And again, it really helps with the decluttering. You can also actually move things. So I'm like, just move it a little bit, so I can kind of see, and just remember that you moved it. But it's kind of helpful. Okay. And visNetwork is actually, at least in the way I've used it here, it can take in different network representations, but I've actually given it, I created nodes and edges and created an igraph object to feed it. And I think it's sort of built with igraph objects in mind. It's also, I mentioned it somewhere up in the text, but you can, there's a, I think an intergraph package that, so you can convert networks from statnet to igraph and back, if you ever need to do that. Okay, so the last thing I wanted, luckily I have time to mention both of the things I had asked about. So, so that's actually, before I move on, any questions about latent net in general? That's the overview of what I wanted to say about it. Okay, so the last thing I wanted to mention, there's another part down here I don't think we're gonna have time to get to, making a dynamic visualization. Oops, there's a typo. I'll let you look at that on your own or ask me questions about it. But just some code to show a co-authorship network evolving over time, which I recently did for a project here. I guess I could show you the output really quick, just so you can see what that does. So I've taken a network, I've divided into time slices, and then I use this NDTV and network dynamic packages to just create this visualization of it over time. I think a couple of people here are specifically interested in like co-authorship networks, so I just wanted to mention that that code is there, and you can look into it. But otherwise, I'll leave this part be. So we'll just, in the last few minutes, talk about A. So I recently came across this package, Netcoin. So, and it's called Netcoin because it's for networks of coincidences. And I think that's probably, some of you are probably from ecology or related fields and work a lot with, if you work with networks, it's probably a lot of coincidence networks is my understanding. That's important in ecology, right? Like species co-occurrence, for example. So I came across this package and I wasn't particularly interested in it for co-occurrence networks per se, but it has this really cool built-in visualization plotting method, which is really easy to use. And what's especially nice about it is that you can share a complete dynamic visualization with someone else without them having to download any software or know anything about R. So I just wanted to illustrate how that works. And so we'll use the Supreme Court data again to show it. So going down to our code, this Netcoin package. Okay, so so I go back to my create my code from my bipartite, kind of works. I don't know, I guess I'm sure there's more than one way to do it. I use SC bipartite to create a socio-matrix, which I then turn into a coincidence object in Netcoin, this package. So I'll just show you what that looks like. And so it's like we saw before, way early on, like 11, Justice 1 and Justice 2 shared 11 decisions, 1 and 3 shared 12 decisions, and this diagonal is the number of appearances of each justice. So that's the data that I'm basing the rest of this on. These co-occurrences or coincidences. So then I do a little reworking. I create some nodes with some information that I want. That's all what all this code does. And then if you remember back when we talked about this data earlier, we were concerned that part of what our model was capturing was just the likelihood that two judges were even on the bench at the same time, as opposed to, are they fundamentally making the same decisions? So, a real principled analysis of this data would actually look at, how many times two justices were on the bench at the same time and control for that. But without doing all that work, we can, when we measure similarity between two judges, we can choose a metric that kind of accounts for that. So, so I'm taking a little pause from creating this dynamic visualization to tell you some of the stuff I'm going to put in it. So, so because this is kind of centered around coincidence networks, they have all these different metrics of similarity that one would use when analyzing coincidence networks. And so I chose this one to focus on because if you go here, A, B, C, D are represented by this table. So A is like both judges made the same decision. B is they made different decisions. And D would be neither were present for this case. So if I'm trying to control for the fact that justices tend to appear at different times, I probably want to just like not use this in my similarity metric, because that's basically like neither judge. I don't want to treat it as the judge made like different decisions or did something differently. Really, they just like didn't even have the opportunity for that case. So I'll focus on the times when they made the same decisions or actively different decisions, if that makes sense. And so that's what I feed into this metric. Now that I've taken that aside to discuss one of the similarity metrics that we'll see in this visualization, I'll continue to make the plot using this allnet function. Again, all the codes here, so you don't have to remember what these are. It's all kind of details, but just the general overview. And this procedures these are actually abbreviations for different similarity metrics that I can include, and that's all in the documentation of the package. But let's plot this now, and then you can see what I'm talking about. All right. So that was really easy, right? It was a lot easier than what I did in visNetwork, actually. Maybe not quite as customizable in certain ways, but pretty easy to go from network to dynamic visualization with all these different features. So the first thing I probably would want to do is change the label. This should probably be like justice name, but I called it label. So now, boom, I can see who all the justices are. Let me make this, spread this out so I can increase the distance between them, or repulsion. So that solves that overlapping nodes problem I had before. I can also, so this, it's kind of doing this like, active fitting physics simulation thing. That's why it's moving around. Let me just stop that. It's kind of annoying. Okay. So let's see. So yeah, I wanted to label the nodes. I know this text is a little small, but I promise they're the judge names next to each node. Maybe I want to color the nodes by the broad religion, and then we'll automatically shoot up a legend here. Again, text is small, but it says like Catholic, Jewish, Protestant. So now I see, at least in this visualization, some pretty strong clustering by religion. I can also have it do its a little kind of built-in community detection. And let me look at religion, which I'm partly focusing on religion because that was, besides difference in birth year, it was the significant factor from our ergo model from before. So you kind of see it's like religion, it seems to be kind of an important predictor of similar decisions. Shape, maybe I want to use, or actually size, I might want to use appearances. Percent. Oh no, so it's already on percent, so that it's kind of scaled to appearances already. And then actually, let me color it by appointing president. So now I kind of have the religions visualized in, coloring's not great, but I've kind of the religions visualized by these groups. And now this is green, these are all blue. Or sorry, these are all green. So you actually also see a little bit of clustering by appointing president too. And then the last, let me just turn this group off for a second, just for visibility. Let me go back to this. Okay, so currently these edges don't really have weights, but let me color the edges by just frequencies. So like these central judges that appeared in a lot of cases have thicker edges between them. And let me look at, let me make the color to be one of a different metric that I didn't focus on of co-occurrence or similarity. Just choose this one. And I'll use this coloring. Okay, so when I do that, it's basically saying, okay, these central, based on this Russell metric of similarity, these central judges that appear a lot and have, are on a lot of cases, they are really similar, and everything else is not that similar. But again, that's kind of our problem that we had before in our first ergo model, right? We want to get past just frequency. So let's try it again with that other metric I mentioned. Okay, and now, like before, the only gray things were between these like central nodes. Now we can, I don't know if you can really see it, but there's like a grayer, and let me actually also make the, I'll make that too. Okay. There's like a grayer edge between Stevens and Souter. So now getting past just frequency, Souter and Stevens are more similar than you might expect in their decisions using this metric, and we can see that. There's also like Sotomayor and Kagan are similar, another kind of gray edge. Scalia and Thomas have the darkest edge, right? They make a lot of similar decisions, especially in First Amendment cases. No one's really surprised by that. And then everything else kind of fades in the background. Ginsburg and Sotomayor, maybe that's interesting as well. But yeah, so just by changing these metrics, you can get a lot of, and Haberman will be similar to the one I just showed you. But by changing these metrics, changing the similarity metric that you use in this network will tell you different information about the nodes. Okay. So yeah, I think this is a cool, easy to use tool, and I wanted to show it to you. It's relatively new as well, and I think with that, I will end. Yeah. Okay. Any questions? Yeah.
So if we wanted to follow up and keep building on our learning, I know there's a Coursera, but it's mostly like social science. Do you have a favorite?
Oh, actually, okay, sorry. One more thing. Not a course, but at the bottom here, the last part of this document has a few more resources. So this first one is just like a huge library of like network analysis software that's available. Next one focuses specifically on visualization. And then there's a book about igraph that you can get for free as well. And then if you're just kind of interested in like the background of all this, not the code, there's this book just called Networks or Networks. Anyway, it's by Newman. I think a new edition just came out, but in the edition I have, I mentioned chapters that align with what I described, but basically it's like a Bible of everything networks, and it's fairly readable, and it's probably, if you're doing a lot of this, it's a good resource to have. But those are more like, you know, ad hoc resources. Because I learned this stuff kind of like over several years on the fly, I don't have like a good recommendation of like one central place to learn it, but those resources maybe are a good place to start. Yeah.
So measurement collections, are you able to access this? And I was just wondering, ability to make it accessible to others. Say if you want to have something else kind of thing on a website, you know, a project, want people to play around. Is there, maybe this is not the time or place, but would you consider maybe a future workshop to tie into that, or is that possible?
Yeah, definitely. Yeah, I guess we have like a submission about, but yeah, let's just talk afterwards. I would be very, very like happy to do more network stuff, and specifically this was, I mean, I tried to cover a ton of stuff, let you know where things are, and you can delve into any of this stuff further, but I would love to do more specific topics based on people's needs as they come up.
All right, we have a space. You're welcome to stay and chat a little bit. If you have a few follow-up questions, thanks so much for coming, and enjoy your weekend.
Okay.